Hi everybody and welcome back to another episode of the Physicist Who Wants to Be a Genius. Before starting this video, someone asked me that how can we know that our calculations or ab initio calculations are true? How can we be sure that our properties are legit and it really express this material? He got me thinking, and the answer of this question, or the answer that I can sleep with, is that the main reason the ab initio calculations were invented by theoretical people or theoretical scientists. The main reason is to start our calculations without any empirical or semi-empirical values. So they are basic. They start from the basic values. For example, atomic positions. So we start from the basics, and have some incredible properties. So it's not empirical. So it's not or nor semi-empirical. This is initial or ab initio calculations or ab initio method. So how to know these results are legit? The only way is to compare with the experiment. This is the only way. And in order to compare, we compare some values, or what values we can cite here. We can compare where is it, parameter optimization, or after a parameter optimization we can compare the parameters or cell parameters from experimental and our calculations. We can compare the band gap. We can compare conductivity. We can compare magnetic moment. We can compare a bunch of things from experiment. So someone can ask me, if we have experimental value, why do we win this DFT in the first place? I can say to him, if we have some values, it doesn't mean that we have a theory. It doesn't mean we have all information about this material. But in the ab initio calculations, the power of ab initio calculations is, if we have one value, we can have all other properties. If we have density of electrons, we can have all other properties. In the case of Wien2K, just saying click. It is incredible. So if we compare, for example, one or two values, and they are exactly or very close to experiment, we can base on them and predict other properties. So for example, if magnetic moment is correct, the band gap is correct, we can say we might have conductivity correct, without doing any experiment, without doing without costing any other money, without costing any value or any amount of money, just by click. It's not easy task though, but it's powerful. Of course, I can miss some points. You can comment them down below. Let me know if you have any answer of this to this man, any answer to me. Of course, I can be wrong. I can miss some points. Please comment down below and enjoy the video.
Okay, so today's video is about the electronic properties of some aeroelastic material based on rare earth element, which is the holmium. A holmium of Z 67 electrons or 67 protons, of space group 225. This data I got them from the Atomic Work website, from this article. After some simple SCF calculations, we can select the charge and total charge here and hit the SCF button. First we will see the charge in sphere for the first atom. Of course, we have only one atom. We have 34 electrons in the upper direction and 30 electrons in the down direction. In total, we have 64.6 electrons under the RMT sphere of the atom. We can see here that we have lost 2 electrons 0.4 or 2 electrons and a half, based on this 67 minus this value 64. So we have lost 2 electrons and a half. So this is for the total charge. For the valence charge, here Wien2K plots only one direction. I think this is the down direction. To see the both directions, both valence charge or valence electrons. First, we will see the electronic configuration for the isolated holmium. This is the core electrons, and this is the valence ones. So we have 21 electrons in the valence charge. To see or to have a deep insight for the valence electrons for both up and down direction, we can go to the SCF2 down and SCF2 up. This is the 2 files that contains all information about electronic excuse me, the electronic properties. So let's open them both. For the up direction, let's stay for the up direction. We have of course, this is for the first atom. Here we can see all atoms in the structure. So if you have multiple atoms, you can see them in the down here. So we have only one. So here we have 11 electrons for the up direction and 7 for the down direction. So if we can, excuse me, if we want to take, or for the other one, if we want to get them both in the same file in order to compare here. So if we sum this 11 plus 7.5, I think it's 18.6 electrons. So 18.6 electrons minus or 21 minus 18.6 electrons, it's 2.4 electrons. So this is the electronic loss after quantum hybridization or quantum effects in this material. Of course, just notice that this material is aeroelastic. This is just for information or a method in order to inform you how we can calculate these properties. For every band we have here, we have for the first atom, of course, we have ESP-DF band and DEG-DTEG. Sometimes this DEG and T2G get also separated for DX2Y2, DXZ2, and other. I think there is 5 bands. All of them lies in here in this line. For this example, it's not there, and their values are zeros, of course. For the S, we have 1 electrons, of course. in every atom or in every band, the s have two electrons, have two electrons, one in the up and the other in the down direction. So let's take this line here and copy it in the other file, just like that. Of course, okay. So we have one electrons in the upper direction and one electron in the down direction for the S sphere or S band. For P we have 6, so we have here 2.8 and 2.8, so about 6 electrons. The D is empty, and the F, of course, holmium is a rare earth element, so there is an F band, so we have 6.9 and 3.4 electrons. The sum of this of all these electrons of all this line, or just to here, all this line is 11 electrons, and the sum of all this line is 7.5 electrons. This is under the RMT sphere. Remember that, it's important. So because in this case the other electrons, there is no interaction between other atoms, because we have only one atom. There's no oxygen or other atom. So electrons must be between the same atom, same holmium. So electrons must be or this electrons, this number count only the electrons under the RMT sphere. So maybe there is electrons in the other, or just near the RMT sphere, are not counted, and this is we can show this for this value, the total charge inside unit cell. So the total charge in the unit cell for the up and down, let's take also this line and put it here, and if we sum this for the up and down direction, we can, if we sum these values, we can find this exact 21 electrons. So there is 21 electrons in the valence in the total unit cell. Of course, it's a mean value, or yes, it's the mean value in the unit cell. So we have here 21 electrons, so there is no loss, because electrons must be in the material, of course. So this loss of electrons in here means that electrons are just separated, or separated from the atom, but they are near the atom. They are not separated, because there is I think there is an effect of the nucleus and on those electrons, so there are in the near the RMT sphere.
So this is it, guys. This is the end of the video, and I hope you like this video. Make a comment, share, please. If you have any questions, please let them in the comments. I like answering your questions. Maybe I don't know all of them, but I try. So bye.